Rosemary Killen is going to speak on chronographic observations of the lunar sodium exosphere. But don't forget that the talk that was interrupted will finish off after Rosemary finished her talk. So please stick around at the end of Rosemary's talk if you weren't planning to. So Rosemary, are you here?
Yeah, do you see my screen?
I see your name.
I should have.
It does not tell me that you're sharing yet, though.
Oh, should have shared.
Rosemary, there should be a second button click selecting the display you want to share.
Oh, do I click on that?
Give me a second, sometimes it'll lag.
I'm not seeing anything
Still
come through
nothing.
just yet.
Share. Screen share has failed. Try. Well.
There we go.
Oh, okay. So let me go back. Okay, so I'll be talking about coronagraphic observations of the lunar sodium exosphere. I'm going to start with my key points. We found that the lunar sodium exosphere is enhanced during periods of high ion flux to the surface, as measured by Artemis, which is pointing to the importance of ion sputtering in refilling the exosphere. The temporal variations associated with high ion flux are consistent with a short e-folding time. And this is actually consistent with the Killen and Hurley paper in 2012. The scale heights to the extended exosphere increase towards both dawn and dusk limbs, and the column abundances in the extended exosphere are minimum at noon and maximum at both dawn and dusk, and I'll try to explain why that might be true. So our observations are taken with a lunar coronagraph out in Sonoyta, Arizona, and remotely operated from either Goddard or from my house. We reported observations that were taken in the spring of 2017, and we have a paper in review for observations in the 2018-2019 observing season. So for those of you who aren't familiar with coronagraphs, the point of a coronagraph is to occult the bright disk of the primary object, which in this case is the moon, so that the dim exosphere can be observed. And so we have occulting disks that can be moved in and out, and we have sodium filters that can be changed from on band, off band. Now, when you're observing the corona, the local time is a function of the phase angle of the moon as seen from the Earth. And so we can get the exosphere is a function of local time and latitude. So this is an example, but you can see these are actually two observations that are superimposed. We take a 10-minute observation with the occulting disk in place, and that's the black that you see. And then we take a half-second observation of the lunar disk. And we found that it was difficult to get the scale height by rotating around the moon. So we used a polar transform so that we can just scale horizontally and vertically to get our measurements. There's a lot of data reduction that goes into reducing the raw data to get the sodium out, but I won't go into that. I've plotted the waxing and waning phases separately because you're looking at different, the exosphere over a different lunar real estate for these two phases. So these are waxing, these are from new moon to full moon. And in general, what you find is if you plot the column abundance with latitude, the asterisks there are cosine functions, just to give you a feeling that the corona doesn't follow the cosine. What our observations begin at about 150 kilometers off the surface of the moon. So we are looking at the extended exosphere, not the near exosphere. And you can see from the left-hand side that in local time, in general, from dawn to noon, we decrease, or from noon to dawn, we increase in column abundance. It isn't one-to-one. You have some outliers, notably the blue, which is morning, is not as dense as noon. But in general, there's this sort of a trend. And the scale heights are also, they vary a lot, but in general, they average around 1,000 kilometers. And that's consistent with a 4,500 Kelvin temperature. Now, I don't believe that temperature is a good model for an exosphere, but just, because people talk about temperatures, that's about what it would be. And for your waning phases, the scale height is also about 1,000 kilometers. It can be as low as 500 and higher, but in general, it's hot, but and 4,500 is actually hotter than most people think impact vaporization. So there probably is a component of sputtering. There's also, this is consistent with what was predicted way back in 1995 by Smith and Marconi. So radiation pressure would tend to increase the scale height towards the dawn and dusk limbs as well. So here you see the opposite trend from noon to afternoon. It increases towards afternoon. And you see, this is a mixture of waxing and waning because we didn't have very many observations in 2019. And again, the variation with local time is a little bit mixed. And for these observations, the scale heights are not quite as consistent, but they're hot. And I'm going to show there's a correlation with Artemis data for some of our dates. On March 3rd in particular, you can see at the bottom where Artemis showed that the ion flux to the surface of the moon, this is in the magnetosheet, then the ion flux abruptly increased, and we measured one of the highest column abundances that we ever saw. So there's some correlation with ion flux, but also February 1st didn't have a particularly high ion flux, but it was near full moon. And as I said, the full moon observations, which we are looking at dawn and dusk terminators, and we have very high column abundances there. So the measured scale heights are on the order of 800 to 1,800 kilometers, but they average at around 1,000. And that's consistent with observations by Cuparacci et al. They used a Fabry-Perot to measure the velocity distribution at the moon. And they also got very high temperatures. The scale heights increased as the moon approaches full phase, but also as it approaches new moon, the scale heights increase. But these are times when you're looking over the dawn and dusk limbs. And I think, like I said, this might be more consistent with radiation pressure than with a different source. And so we do have exceptionally high abundance associated with high ion fluxes and with full moon. And the data are consistent with a minimum near noon, which I believe is also consistent with radiation pressure. So I'd like to acknowledge NASA Solar System Observations funding, Dream 2 and LEADER. And I had students from Howard University, and they were funded by the Minority University Research and Education Project. And a student from Embry-Riddle was also funded by my solar system observation. And we thank Artemis for their data. So just to show you where the telescope is, it's in Arizona on the high plains. It's not on a mountain, but it is at a high elevation and very in a very remote area. So there's only one person who lives nearby, and they sort of take care of logistics of internet and so forth. And there we are. So that's what I have, and I'll take questions.
Fantastic. Rosemary, thank you very much for that talk. We do have time for a couple questions before we move on to our newly last talk. Let's see, I'm looking on chat and do not yet see one. Let's wait another 30 seconds or so before we move on to our last talk. Again, Rosemary, thank you very much.
Thank
Nice
you.
talk.